Welcome everyone to the week of mini courses on group-theoretic mathematics. I'm really excited to see you all here, and all of us who've been working largely over email to make all this happen, and we're super excited that you're all here. So a couple of very general announcements before we begin with the math. So first of all, the mini courses that you see this week will be participant free, hence the homework that Nathan already put on the web. There are homework problems. Please do them. They'll be fun. There will be review sessions or problem sessions. Discuss problems and discuss questions about this material. The first one of these will actually happen at the end of this morning, just because the first one of Nathan's talks is going to be so introductory to the whole general topic. So the one this morning is a very general opportunity to ask questions about the setup for people who might not be as familiar with with three manifolds who might be coming from the world of group theory or vice versa. So please come to the problem sessions. Please participate in the problem sessions. Accordingly, we have we have one wonderful TA associated to each of the mini courses. For the two people who are going first this morning, for Nathan's talk, the TA will be Adele Jackson. So please come to Adele with questions if you have questions. And the TA for Ian Beeringer's talk is going to be Riley Lyman. Come to Riley, and they will also be leading the problem session. The other announcement is that we plan to have a bunch of lightning talks. The more the merrier. I think I and several other people who are in the room were at a workshop in Overbold a few months ago, and another one in New York, where there were lots of teeny tiny lightning talks by people up and down the seniority scale. It's great. It's a wonderful opportunity to talk about a snippet of what you're working on, or even a problem that you're interested in. It does not have to be a result. It can just be, hey, here's a cool thing. It's a great chance to introduce yourself. So please email me a lightning talk title if you are interested. Just send an email to me with the words lightning talk in the title. Everyone can do it. People who are also giving a separate talk can do it. People who are just starting graduate school can do it. So please send me an email to that effect. The intent is for the first one of these lightning talk sessions to happen at the end of the afternoon tomorrow. So by the end of today or early tomorrow, then we will make that happen. I think that's all the announcements I have. So with that, I think I'm going to let Marco on.
Okay, so kicking off the week, today we have Nathan Dunfield, who's going to give us an intro to basic topology and geometry for three manifolds.
Hi, well, thank you. The purpose of this talk, I guess technically it's not part of the mini course that I'm giving. This is supposed to be kind of just general background on topology of three manifolds and their geometry, sort of for those of you who come from more of a group theory background, so that we all have sort of some common knowledge. Okay, so in that spirit, please interrupt me at any time with questions. Otherwise, I'll just keep talking faster and faster. All right, so I'm going to talk about things in dimension 3, but in 2 dimensions, the fundamental groups of surfaces are very highly constrained, right? So up to finite index, if we take the fundamental group of a compact surface, so this is, well, it could be the trivial group if it was the sphere. The annulus would give us Z. The torus. If we take a surface with boundary, like a pair of pants or something, its fundamental group is free, so that's finite index in the free group of rank 2. I guess the only remaining one is the fundamental group of a closed surface of genus 2. So in terms of the groups themselves, in 2D, it's highly restricted. And in higher dimensions, I'll just say 4D. 4D is confusing enough for me. Any finitely presented group shows up as the fundamental group of a 4 manifold. So any finitely presented is the fundamental group of a, closed, smooth. I could throw in symplectic if I felt like it. 4 manifolds. And what happens in 3D is somewhere between these two extremes. And that's what I guess we'll be learning about this week. And I mean, for example, just like what's one kind of group theory fact about three manifold groups? I'll call this a corollary. I'll eventually tell you what's corollary of. So if we look at the fundamental group of a, I don't know, let's say compact three manifold, then this group is residually finite. Meaning it has lots of subgroups of finite index. Specifically, if you look at the intersection of the finite index subgroups in G, this is just the trivial group. You look at subgroups of finite index. In particular, this is saying that any non-trivial element you can sort of see as non-trivial in some finite quotient. Anyway, this is a property that's certainly not the case for an arbitrary finitely presented group. And there are many finitely presented groups, even ones with non-positive curvature or something, that have no finite index subgroups at all. So the question then is, if three manifold groups are special like this, where is that coming from? And that's kind of what I want to tell you this morning. Other questions? So kind of basic fact that we need is that in 2 and 3 dimensions, we don't have to worry too much about the distinctions between smooth manifolds or piecewise linear manifolds or topological manifolds. In 2D and 3D, any manifold has a unique smooth structure, unique piecewise linear structure. So, we'll just regard sort of my convention. Then for concreteness, I'm going to regard all my manifolds as smooth. All manifolds maps are smooth. Not that I'll ever sort of really use this in some sense. I mean, I will, but not in any concrete way. I'll never take a derivative if I don't have to. But maybe I should have said this before I wrote my convention. This is very much something specific to these low dimensions, right? So in 4D, for example, even R4 itself has uncountably many distinct smooth structures. There's uncountable collection of smooth 4 manifolds whose underlying topological space is R4. This is the only dimension in which this happens. Okay, in all other dimensions, there's only one. Milder things happen in other dimensions, like there are 28 smooth structures on the 7 sphere, and so on. But in our dimension, we don't have to. What we're talking about, we won't have to worry about that kind of phenomena. And another convention. So I'll always be thinking about smooth manifolds, and certainly all 3 manifolds I'll talk about are orientable. In fact, I'm going to actually orient them. And they're usually closed, so they don't have any boundary. They're compact and no boundary. Sometimes I'll allow them to have boundary. If it's not clear from context, just ask. So not a lot of board space here. But I've already posted the lecture notes for this lecture online at that URL. And having said that, now, if I see anyone out there checking their phone, I can think, they're just looking to see what I said on the last page. But anyway, I do have to erase quite frequently. So, there's this basic, in any dimension, there's this basic operation on manifolds of connected sum. Let me explain how that works or how that relates to 3 manifolds. So I mean, just, pictorially, right, connected sum, you start with 2 manifolds A and B, and you pick a point on each manifold. And then you remove a little open ball about those points. And then you take the two boundary spheres that result, which are circles in this dimension, and you glue them together. In this case, we would get something like this. And you can check that this doesn't depend on which point we pick, and it doesn't depend on the particular open disk we choose to delete. It does. There is a choice, though, when I'm gluing here, on how I glue the boundaries together. In particular, I could choose to do this by an orientation preserving and orientation reversing map. Those are like fundamentally different choices. And that's part of, so all my manifolds are actually oriented, not just orientable. So when I do something like connected sum, I'm always going to do it so that the orientations of these two things piece together to give us an orientation on this. So that's actually making this kind of well-defined now. And so, of course, you can always, if I took this thing here to be just a sphere, right, if instead of using this, I had picked a sphere as my second manifold, right? Well, then I wouldn't have done anything interesting. And so we can always take a manifold and write it as sort of a connect sum in this kind of trivial way, where one of the pieces is a sphere. So we'll say a three manifold is prime if, put it this way, M is prime if whenever we write it as a connect sum, one of the pieces is a sphere. And so some examples of what are some examples of prime three manifolds? Well, the three sphere itself is prime, as is a lens space. Something like the three-dimensional torus. I don't know, surface cross. We take a surface of genus G cross a circle, where here G I want at least one. Don't want a sphere there. Well, that's okay, actually. I don't care. Spheres are fine. I don't know, the unit tangent bundle to a surface. Many of the three manifolds you probably encountered first in like algebraic topology class, they turn out to all be prime. And you probably ask why. And the answer is one of the first problem on the homework sheet for this lecture. But they do exist. So we have this natural operation that allows us to take two manifolds and combine them. And in three dimensions, I mean, we have these sort of prime pieces, prime things. And it turns out we can break up any three manifold into prime ones. And this is one of the important, this was proved by Naser and Milner. Well, Naser showed existence and Milner showed uniqueness. So any, let's say, closed three manifold can be written as the connect sum of prime three manifolds. And this is a unique up to, of course, I guess I can permute the factors. So the first step often handling any question about three manifolds is we will look at it for the prime pieces and then reconstruct the final answer. So typically we'll be looking at prime manifolds. So this is about group theory, right? So let's think about what is the fundamental group? How does it behave under connect sum? So in my old picture, when I had a torus here and I got a two-hole torus, you might think that connected sum is going to do something interesting on groups, because then it took, these two things were abelian groups and it somehow turned it into a non-abelian thing. But we're in a higher dimension here. So the thing I'm going along is actually a two-sphere. So they're simply connected. And that tells us what about the fundamental group of this Yeah, it's a free product, right? So they're gluing along a simply connected thing. Van Kampen tells us that this is a free product. And actually, this is the kind of pattern we'll see repeatedly in this talk, is that you can go backwards. So Stalling showed, so I should say his theorem was proved like 1930. Okay, so this is quite old. Uniqueness was Milner, that's later, but existence was Naser. So Stalling showed in late 50s that the converse of this is true. So in particular, so if the fundamental group of a three manifold is a free product, then M is in fact the connect sum of two three manifolds whose fundamental groups are the gamma i's. So the connect sum really respects this basic group operation. And again, so then that's one way we'll reduce if we want to know something about the fundamental group of a three manifold. Well, that's the free product of fundamental groups of prime manifolds. So we're going to then be able to like focus on the prime pieces.
The unique there, is it also for the spheres that cut?
No. So yeah, that's a great question. So it's not actually a unique collection of spheres. It's a unique collection of these manifolds. So there's like, let's see, where's a good picture? Place to draw a picture. But I thought they didn't get recorded. Okay, well then I can use it. But maybe it's, I don't know, I'll use it for this picture. So right. So the thing is, here's a picture of a connect sum of three manifolds, but somehow you also have this picture. Maybe this is not quite. Well, I guess in this case, the sort of middle piece is the a sphere. So maybe I'm kind of cheating here. But in particular, if these, okay, how about I do this? So here we have the connect sum of surface of genus 1 with a surface of genus 2 with a surface of genus 1. Here's the same thing, right? But somehow the set of spheres here that I'm dividing along are different, right? Because in this one, it's the thing of genus 2 that ends up with two things, whereas here it only has one. So this collection of spheres is not unique, but the pieces are. And as you permute them, you change like how the spheres sit inside each other. Other questions? I can't, you're the organizer. How can I stop you?
In Stalling's theorem, does the inclusion of this function AIs into M's realize the three vectors?
Oh, yeah.
So you can realize everything.
Yes. I think it's probably only dimension 3, yes, but I'm not sure. Certainly, this just assumes that dimension is bigger than 2, right? But I think this should be probably a 3-dimensional thing. And we'll come to that actually, or something related to that in just a moment. But I realized I wanted to kind of getting ahead of myself. I wanted to say that there's a notion. So we have these prime pieces, but there's a notion that's slightly stronger than being prime, which is irreducible. So a 3-manifold is irreducible when every embedded 2-sphere bounds a ball. I mean, this tells you it's prime because, if it's not prime, you have this sphere which separates it up into A and B, right? That's a particular sphere that doesn't bound a ball. And in fact, so this certainly implies prime. And they're almost the same to the point it's kind of annoying we have to have two different words. The only prime but not irreducible manifold is the product of the two sphere and the one sphere. Only prime, but reducible, I guess. You're probably wondering why that is. That's problem 2. So in fact, the examples I brought up earlier of prime manifolds, they were actually all irreducible manifolds because they weren't S2 cross S1. And it turns out, as you'll see from homework, that somehow this is, in some sense, easier to check. So we'll typically deal with irreducible manifolds. Okay, so one thing that's special about dimension 3 compared to higher dimensions is that there are ways, so this is kind of a theme, 2D and 3D, is you can often promote, I give you like a homotopy equivalence between manifolds. Then in these dimensions, we can often promote that to an actual homeomorphism. Or given two homeomorphisms that are homotopic to each other, you can often promote that to an isotopy between them, a homotopy through embeddings. So I don't know, just promote to embeddings. So I'll just give an example here instead of being so vague. So one of the really important classical theorems, this was proved in 1960 by Papakirakopoulos, and it says the following. So if we have a 3-manifold whose second homotopy group is non-zero, so that just means that there exists an essential a map from the 2-sphere into the 3-manifold, which is not homotopically trivial, which is not homotopic to a point. If this, then there is an embedded 2-sphere, which is non-trivial in pi2. So you should think of this as we have our sphere, it's mapping into our 3-manifold some horrible way. It's not even an immersion, just some map. But this map, we cannot contract it to a point. Then what the sphere theorem says is that there's another map, and it might not be homotopic to F. This is like a little caveat. So that, which in fact, it ends up being built out of pieces of this map in some sense, where this new nice embedded map, embedded sphere is also, it's not homotopically trivial. We can't contract it to a point. So in particular, this is saying that, so the thing is, like, we have some interesting map of our sphere into this 3-manifold. And well, that's a very interesting fact, kind of on the level of homotopy theory, but it doesn't allow us to do anything to our manifold, right? It's just we have this map and its image is some crazy mess, right? But the sphere theorem and its companion, the loop theorem, which is similar in nature, says that actually you're allowed to replace that with an embedding. So like in particular, this is saying a corollary, if M3 is irreducible, then pi2 of M is trivial. And again, this will be homework. If we have an irreducible manifold and the fundamental group is infinite, then in fact, our 3-manifold is an Eilenberg-MacLane space. So then M is a Eilenberg-MacLane space for its fundamental group. So in particular, the same as saying the universal cover is contractible. So already this is saying that for irreducible manifolds, we've washed out all of higher homotopy theory here. And we're really just dealing with Eilenberg-MacLane spaces. Oh, you certainly do not need geometrization for this. So this is really just a corollary of the sphere theorem. This was known long before geometrization. Okay, so that's a great segue actually, because so that's just this is topology of 3 manifolds, like through 1960 more or less. the other thing I need to tell you about today is sort of the role of geometry. Again, to put this in perspective, in 2 dimensions, right, every closed surface has a metric of constant curvature, right? And we have the round sphere. That's the last one I can sort of draw geometrically. We have the flat torus. So of course I want to draw this picture, but this has both positive and negative curvature. So, really I want to think about this maybe as the quotient of the Euclidean plane by a lattice. And then higher ones are sort of hyperbolic, coming from tilings, polygons. So we'll come back to that. Anyway, this is the uniformization theorem, I guess, complex analysis. That's great. What about in higher dimensions? Well, I mean, of course, what do I really mean by geometry? So I'm kind of thinking not just like having a Riemannian metric. Of course, any smooth manifold gets one of those, but something that's sort of locally homogeneous. So something that looks the same locally at every point. So constant curvature is certainly going to count as geometry in my book. Some other things do as well, but not just a general Riemannian manifold. And so in 4 dimensions, no matter how much you stretch the notion of being homogeneous, homogeneous geometry is extremely rare. And it's very interesting, hyperbolic manifolds, for example, in higher dimensions. But it's sort of, but what you learn about that does not tell you much, if anything, about sort of the general world of 4-dimensional topology, right? And the reason for this is just that, as I said, any finitely presented group is the fundamental group of a smooth closed 4-manifold. And once you have a homogeneous geometry, as we'll see later in my mini course, that gives you a lot of sort of special algebraic properties that are not true of sort of generic finitely presented groups. Okay. So what about 3D? That's what I'm supposed to be telling you about. Well, okay, so it's not the case that every 3-manifold has a metric of constant curvature, right? So for example, S2 cross S1 does not. And well, one way to see this is the universal cover of S2 cross S1, right? Its universal cover is S2 cross R. And come back to this in more detail, but if you have a metric of constant curvature, when you go to the universal cover, then what you get is the simply connected space of constant curvature. In that dimension, there's only one, right? So you would either get, for example, in 2 dimensions, you would get 2-dimensional Euclidean space, a 2-dimensional sphere, or some kind of 2-dimensional hyperbolic space. And this thing here, so in particular, if this had a metric of constant curvature, this would need to be topologically either the 3-sphere or R3. And it's not. So just, it can't have any. On the other hand, you look at this and say, well, okay, it doesn't have metric constant curvature, but this has a very nice metric, right? We take the round metric on the sphere and the metric on S1 and take the product. That's locally homogeneous. Okay. So we're kind of not out of luck yet. And in fact, the kind of shocking thing is that we're in luck. So there actually turns out to be enough geometry to go around to, in some sense, cover all 3 manifolds. And that's the content of the geometrization theorem, which is what I need to tell you about now. So this perspective on 3 manifolds was introduced by Thurston starting in the late 1970s, and was proved in full by Perelman in 2003. Contributions by many others. Just tell you what it says. So, and I'll have to explain a couple of these terms. I'll do that over there. Any closed 3-manifold, oops. So let's say, as I said, we always look at, go ahead and break it into the pieces. There is, of course, one irreducible prime manifold. It's not irreducible, which is S2 cross S1, but we already said it has a nice metric. So that's all good. Any closed irreducible 3-manifold can be decomposed into pieces along, not sort of along arbitrary things, but decomposed along what I'll call incompressible tori into pieces. So these pieces are going to have a nice metric, like a flat metric or metric of constant curvature, or something slightly more general. So into pieces that admit Riemannian metrics modeled on one of 8 possibilities. So it could be just the flat 3-dimensional Euclidean space, could be the geometry of the round sphere in R4. There's hyperbolic space, we'll come back to that. So those are the constant curvature ones. Or we could have, well, we could have something like S2 cross R. That's a nice homogeneous metric. We could take the 2-dimensional hyperbolic plane cross R. There are 3 more. These come from certain Lie groups, 3-dimensional Lie groups. There's a nilpotent Lie group, a solvable Lie group, and the universal cover of the Lie group SL2R. But in particular, these being Lie groups, they have a left invariant metric. So in particular, they're not homogeneous. Yeah, so that's in some sense, maybe I don't need this geometry. There are other manifolds that have this geometry. Well, there's not very many of them, actually. So I might, in fact, not need this here. Maybe I should have said prime. Why do we say prime? Because it gets enough trouble being the only prime but not irreducible manifold. We shouldn't exclude it. I feel bad about it, So now it's included. Now we definitely need that one. What I need to tell you about this decomposition, right? So this is what do I mean by here, sort of incompressible and decomposed. I mean, these are key. Now, I mean, of course, if you're encountering this for the first time, you should just pretend I didn't write any of that. And what I'm saying is that lots and lots of 3 manifolds have a homogeneous metric modeled on one of these 8 things. Like either they have constant curvature or they have something that's maybe slightly more complicated than constant curvature. In particular, it's saying that if we're going to be studying 3 manifolds, we're going to have this sort of rigid geometric structure, or potentially sort of rigid. Anyway, it's a metric, it's rigid. This sort of geometric structure that we can use. And in fact, I start off with this, what I call the corollary, that 3 manifold groups are residually finite. It's a corollary of this theorem. That it seems kind of remarkable that this doesn't seem like something that's going to tell you about the fundamental group, but as I'll explain eventually, my mini course, it does. Okay, so what does incompressible mean? Incompressible, this is generally for a surface. So a surface embedded in a 3 manifold is incompressible. And let's just make this connected, oriented. Is incompressible if, well, I don't want it to be the 2-sphere. We're always in a situation where we're prime, so there aren't very many 2 spheres. But here's the real condition. If you look at the map on fundamental group from pi1 of f into pi1 of m, this is injective. Right? So in particular, this is not, these tori here, they're not just like, oh, here we are in R3. Here's a torus. Woo. Right. Here, the map from pi1 of this torus into pi1 of R3 is the trivial map. This doesn't tell us anything really about the topology of this manifold. Okay, so we're interested in that. So we're interested in, so in particular, these are ones that actually correspond to z-squared subgroups of pi1 of m. Sort of, decomposed. So we're sort of, this is something called the Jacob-Shalin-Johansson decomposition. I'm actually going to talk about this in my mini course a bit. So for now, we'll just say this is like a prime decomposition theorem, except now we're decomposing along these incompressible tori instead of along spheres. But in particular, it's a unique there's some kind of unique, purely topological decomposition that's going on that gives you these pieces. Right. So by far the most important geometry and also the most common is the hyperbolic geometry. And so in particular, manifolds that emit the other 7 geometries, they're completely classified from sort of a purely topological perspective, and we understand them very well. Which is not to say that every question you could ask about a manifold with those things, you immediately know the answer, but you have a huge, it's kind of like a surface, you know, there's not every, like you don't know everything about surfaces, but you really have a good place to start. Whereas this, as we'll hear about some of the other mini courses, Ian's course in particular, Michelle's course, we don't really understand what's going on here in that level of detail. It's just so much more complicated, probably we never will. So then what I want to do now is just talk about examples of hyperbolic manifolds to kind of get us started. So maybe I should pause before I do that. Are the questions about geometrization? Yes. So it's a great question. So why do we need these? Why are we cutting on the Torah at all? It'd be much simpler if we didn't have to. I guess let me say that the reason, and I'll go into this in my second lecture today in detail, but the reason is hyperbolic manifolds, let's say closed hyperbolic manifolds, they don't have any z-squareds in their fundamental group. They don't have any tori in them. So if I build you a manifold with an essential torus, sorry, incompressible torus, I'm not going to be able to make that be hyperbolic. And so if it's not super special and falls into one of these forms, I can't geometrize that piece. So it's instead that we need to, I guess that's the answer. But that's because, yeah, hyperbolic manifolds are kind of allergic to tori. So other questions? So, all right, so we want to talk about examples, right? So we want to talk about hyperbolic geometry. And so, all right, so lots of ways to think about this. So we could think about, say, the Poincare ball model. So here, the hyperbolic space is just the, so topologically, it's the interior of the unit ball in R3. And it has a funny metric. So this is going to be the Riemannian metric. It's a multiple of the Euclidean metric, which is to say that angles in this picture are accurate, but distances are wildly distorted. So in particular, if I have a little object here in the middle, as it moves away from it, it will appear to us to be getting smaller and smaller and smaller. Right. So this r squared, this r is the distance that we are from the center, like we're working in spherical coordinates. So as r approaches 1, as we approach the boundary, this thing blows up, which is to say very small things are actually very large. So this is it as a Riemannian metric. And what do we know about this? So like we know, for example, what geodesics in this space look like. Geodesics in this space look like, so the boundary is not part of hyperbolic space. It sort of plays a big role in this when we study it, so it's a little confusing, but it's not actually there because the point is if you go out along a straight line and you integrate that quantity, you'll find that it's infinite. Okay, so the boundary is infinitely far away, but geodesics are best described, despite this, as sort of circles which head out to the boundary at right angles. So maybe you're more likely to have thought about maybe the two-dimensional hyperbolic space, like the Poincare disk model. There's lots of copies of that sitting inside this. So this doesn't look like it from this description, but this is actually homogeneous. So given any 2 points, there will be an isometry that takes this point to this point, just like in Euclidean space. You take any 2 points, there's an isometry that translates from one to the other. So this actually is homogeneous. And so, you have this, here's a copy of sort of the two-dimensional hyperbolic space inside it, but there are lots of other copies, and they may be, I'm not very good at drawing them. Here's one. That's another copy of hyperbolic space, two-dimensional hyperbolic space. And the geodesics in here, again, there's circles meeting the boundary at right angles. There's lots of amazing properties about these, like, triangles have angles that are less than pi instead of equal to pi. Anyway, we'll see some of these in various of these courses. And so, okay, this is sort of hyperbolic space. And so this is homogeneous. Oh, and I should also say this is actually clear enough from the formula. It's also isotropic. So that means that, like, if we look at isometries which fix this point, like if we just take any rigid Euclidean rotation that fixes the origin, right? That will respect this metric. It doesn't matter how we rotate at the origin, we're just going to see the same thing. And then if you buy this homogeneous, then this is like the most symmetric thing you can imagine. It's just as symmetric as Euclidean space. Okay, so this is a nice thing. So what's a hyperbolic manifold then? Well, or a three manifold, I guess, because I'm kind of thinking about dimension 3. Is one, well, there's two ways I could describe it, so I'll give both. Is one where with a metric of constant curvature -1. And I guess let's just insist this be a complete metric. So that's one way of thinking about a hyperbolic manifold. But another way, alternatively, we can think of the manifold as, so I mean, let me put it this way. If I had a manifold like this, and I go to its universal cover, okay, its universal cover, it's a simply connected manifold with constant negative sectional curvature. Hadamard's theorem tells you that universal cover is in fact H3, isometric to H3. So we had our manifold like this, and here's its universal cover. Now the deck transformations of our covering map, those are all going to act by isometries on this, right? Because the metric here is actually pulled back from the base. So alternatively, we could think about our manifold as we're taking the three-dimensional hyperbolic space. Its fundamental group is acting on this by isometries, and we're taking the quotient. So we can think about this as the quotient, where here gamma is a group of isometries of H3, acting freely, properly, discontinuously. So, I mean, in other words, it's like when we think about the torus, right? We think about this as take two-dimensional Euclidean space and maybe take a lattice. I should just draw the square lattice. So that's the one I can draw. We have this nice square lattice. We have z squared here acting on this by translations. And we think about this as the quotient. So this is really the picture you should think of, except we just replaced this with some more exotic geometry at negative curvature rather than flat. Okay, so well, all right, but maybe for this to be sort of useful, I should say, what are the isometries of hyperbolic space? And I'm going to be thinking about the orientation preserving ones because I'm only thinking about oriented manifolds, right? Well, the answer is, it turns out that these isometries, so they're maps of the interior of this ball, the open ball, but they always extend continuously, it turns out, to a map of the sort of sphere here, which is called the boundary at infinity, the sphere at infinity. The map that the isometry gives to the sphere at infinity is actually a Mobius transformation. So we view this sphere as sort of like the Riemann sphere. Then this works out to be the group of Mobius transformations, orientation preserving, of the boundary. When Well, Mobius transformations, those are things that look like, complex notation z goes to AZ plus B on CZ plus D. That's encoded by a little matrix, right? A, B, C, D or something. And it turns out that this is then isomorphic to just 2x2 matrices. We could normalize them to have determinant 1. And so this group, this is the fundamental group over manifold, is actually in here. It's actually a bunch of 2x2 matrices. And as I'll eventually explain, the corollary that things are residually finite is in the end going to come from the fact that we really have a group of matrices. And that's a very concrete object. Okay, so I'm just going to give a couple examples, but I think I'm going to have to delay those till my second lecture. But I want to make sure I emphasize something that is also the sort of very specifically three-dimensional. So when I talked about the geometry of manifolds depending on the dimension, right? We saw that in 2 dimensions, every closed surface has a metric of constant curvature, right? But in fact, typically it has many, right? So if you look at a surface of genus G, if G is bigger than 1, it has a hyperbolic metric. And there's actually a whole space, the Teichmuller space or the moduli space of different hyperbolic metrics on that surface. It's dimension 6G minus 6. There's many interesting questions that you can ask about that space. So there's dimension 2, I guess there's sort of more geometry than there is topology, right? The topology, we know what all the fundamental groups of surfaces are. What's interesting is their geometries and also the dynamics. So just because those groups are simple doesn't mean their automorphism groups are simple, right? The mapping class group is the study of self-homeomorphisms of a surface to itself. That is a very interesting object, but even though it's acting on kind of a simple group. But so in dimension 2, there's way more topology. Sorry, there's way more geometry than there is topology. And in dimensions 4 and more, there's way more topology than geometry. 3 is the magic middle. So Thurston's mantra is that topology is geometry in dimension 3. And well, the geometrization theorem said we had a lot of geometry, but what am I sort of saying is here? That's because of another really important theorem from the 70s, which is Mostow rigidity, which says the following. Suppose we have 2 hyperbolic manifolds. Well, they could be closed. Let's just say closed. And at least 3. This is a very important question. Sorry. Depends a little bit on, well, yes. Let's just go with yes. I mean, well, it sort of depends on what you mean by tell me what it is, right? I mean, its entries are numbers. You got to have to sky how does there's algebraic numbers? Are these something like you give me a Turing machine that can compute the entries of the numbers? But yes, within limits. The answer is closer to yes than no. Certainly I can come back to that in the later talks. So if these guys are, then if pi1 of m is isomorphic to pi1 of n, this is just as groups, just as abstract groups, nothing, then m and n are homeomorphic. They're actually the same space. Actually, we can say more. They're diffeomorphic, which, in high dimensions is actually not automatic. In fact, they're isometric. There's an isometry between m and n. So just knowing their fundamental groups are the same, the geometry is completely locked in. And what that means then is that, to come back to what Thurston is saying here, that means that any geometric invariant of a hyperbolic manifold, let's say 3 manifold, just going on small-minded like that, is a topological invariant, because there's only one hyperbolic metric if you have one. So for example, good place to end. Here we have a knot in the 3 sphere. So it's a bedding of S1 into S3. And let's say we delete this knot. This turns out to be a hyperbolic manifold. It's not compact, you should argue, but it turns out it's got a metric of finite volume, which is almost as good, sometimes better. And the volume of this is approximately 2.02988 something, something, something. It's a number that's conjectured to be transcendental. No one can prove it. But the point is that this number is actually associated to just this picture. And so one of the major themes of ongoing work in this field is to understand the relationship between the geometry and the topology. So Mostow, so geometrization says you have lots of geometry. Mostow says the geometry is unique, but that doesn't mean that you can easily stare at this picture and say, of course, it's 2.02988, Nathan. What else could it be? So I think that's a good place to stop. Yeah. So right. So I kind of focused on closed manifolds. Something like this, right? There's a torus sitting in here, which is going to sort of seemingly contradict what I was saying about no tori, right? There's this in the exterior here. There's this nice torus, and this is actually coming from, and we'll get into this, I think, my next talk. But so, okay, let me just draw it this way. Hyperbolic space. And we already saw there were copies of like 2-dimensional hyperbolic space in here too. If instead we look at a sphere, sorry, which is tangent to the sphere at infinity. And so this is what's called a horosphere. Now topologically is not a sphere because the point at infinity isn't there. So this is actually a copy of R2 topologically, right? It's a sphere minus a point. And the interesting thing is it's not just topologically, it's actually Euclidean space geometrically. So it turns out, and maybe we can work this out in a subsequent lecture, but the geometry here, this is actually isometric to Euclidean space. And I really should have made this red. It was hard to see, but also because it should match this color here. So this torus does end up with a Euclidean metric. It's coming from this horosphere, which is not totally geodesic, right? So this is totally geodesic. This is sort of curved, but it's sort of a uniform way. So it's like constant mean curvature 1 or something.
Off the topic, so look at isometric group of the edge 7 models.
Oh, yeah. So of course each one is a little different. But for the sphere, well, it's just the orthogonal group on 4-dimensional orthogonal O4, right? For Euclidean space, it's like the affine. It's not the affine group. It's what's it going to be? For if we're doing Euclidean space, it's O3 semi-direct R3. That would be the isometry group. And for the other ones like nil and sol, it's actually bigger than nil and sol. It's like they act on themselves by left translation. That's not the full thing. There's another dimension that comes in. So one of the things I have on the website is some references that will include descriptions of each of these geometries. But it's like I kind of work them out one by one. The article by Peter Scott, Geometries of 3 Manifolds, is a great source if you want to learn about each of these individual geometries. Yes, so right. So that's a great question because, how many closed 3 manifolds are there? The answer is there's countably many, right? Because they're built from finite triangulations. There's countably many ways to stick these things together. And so there's not like a kind of completely natural way to sort of sample from the set of 3 manifolds, right? There are various, you can define some kind of notion of random 3 manifold, various ways to do it. And they sort of don't necessarily all behave in the same way. But there are models of random three manifolds, which you can actually prove a theorem, which is that a generic one is hyperbolic. Also, so I maybe a good just sort of direct evidence here. Here we're looking at these knots, right? And this one's a hyperbolic knot. And it turns out knots of less than 20 crossings, of which there are 350 million prime knots of less than 20 crossings. I think all but 100 are hyperbolic. Okay, so certainly in the range of examples we can think about, it's often overwhelming.
With the number of crossings that may go into approaching to infinity, the manifold is going to be not hyperbolic.
So who did?
And be Maluthian from the center of the board.
Not aware of
Results
this.
that the proportion of hyperbolic ones does not approach 100. There's like at least 10 to the minus 17 of them that will be, right.
Yes, yes. Well, that knows right. So, and this comes back to how you choose to define random. But what should happen even in that situation is that there's a very large hyperbolic piece. So you know, again, we have this decomposition in tori, which you haven't talked about. So if you draw an incredibly complicated knot, then there may well be pieces that are not hyperbolic, but they will sort of be small, and the largest piece will be hyperbolic.
That beautiful artificial model doesn't actually reflect human experience. Human experience has most knots, such as the truck oil knot, or the hexagon, or the circle knot. And if you're really lucky, you get a figure 8 that doesn't have.
So I will attempt to convince Danny in the next talk that this is not that he needs to broaden his range of human experience.
Hi, everybody. Next week we'll go to Nathan's garden and check out his garden hose.
I live in an apartment. I have no garden hose.
Question. From the app, what does as groups?
Oh, just, I mean, isomorphism of groups between this group and this one. Just as abstract groups.
Let's thank Nathan again.